Here's problem number 11. It says, which of the following molecules are polar? So I'll write them down as I read them. There's Cl2, carbon dioxide, BF3, nitrous oxide, SO2, and xenon tetrafluoride. Okay, so when we're talking about polarity, what we mean is differences in the distribution of the electrons or the electronegativity in the molecule. And what you'll find is that if you have a symmetrical division of the electrons, then the molecule is not going to be polar. So in this question we're looking for polar molecules. So a good tool for looking at the polarity of a molecule is by drawing the Lewis structure. So if we start with Cl2, for example, the Lewis structure of Cl2 is pretty simple. It's just Cl bonded to another Cl. And there's 3 pairs of electrons around each chlorine. So is this polar? Well, we have, as you can see, there's a perfectly symmetrical division of electrons. This molecule is not polar because you can't draw like an arrow where the distribution of charges are. This molecule doesn't work like that. So chlorine is not polar. So what about carbon dioxide? Well, what does the Lewis structure of carbon dioxide look like? It's composed of a carbon and 2 electrons. The carbon's going to be in the middle because it's the least electronegative atom. So we'll bond it to oxygen, oxygen. It actually has 2 double bonds with 2 lone pairs on each of the oxygens. So in this Lewis structure, it's a good one, you can see, because all of the formal charges on the atoms are 0, and the octet rule is fulfilled for every atom. So how about this? Well, this molecule has a linear shape, and once again, you can see that the distribution of electrons is perfectly symmetrical, no matter which way you divide the molecule. And also, the molecule has a flat linear shape, so there's no polarity in carbon dioxide. So how about boron trifluoride? Okay, well, that's a boron with 3 fluorines attached to it. Just make sure that's right, yeah. So this boron does not have any lone pairs, whereas these fluorines all have three lone pairs each. So this is actually a trigonal planar molecule. There's no lone pairs on the boron, and it has 3 atoms all the same on it. So the pull of electrons is going to be this way for all 3. One fact about trigonal planar molecules is that all the bond angles are even. So the electrons in this molecule are, once again, they're all perfectly symmetrical. So this molecule is not polar. So what about nitrogen oxide? Well, if you think about it, there's only 2 atoms in this molecule. Unlike the first one, which was chlorine-chlorine, there is no polarity there because the atoms are all the same. But if you have a molecule with 2 different atoms, that has to be polar, right? Because the electronegativity is going to be different from one to the other. Like, even if it's a tiny difference, that molecule is going to be polar. So nitrogen oxide is polar. I'll complete the Lewis structure for those who are curious. It'd be This, I have to use up 5 plus 6. 5 for the nitrogen plus 6 for the oxygen equals 11 electrons. So 2, 4, 6, 8, 10, 11. But yeah, that is polar. And since the oxygen is more electronegative, the polarity bar would look like that. Okay? So next is SO2. S is the least electronegative, so it's going to go in the middle. We're going to have an S connected to 2 O's like that. So how many electrons do I have to use up? 6 for the sulfur plus 6 for each of the oxygens equals 18. So if I make some double bonds, that's 2, 4, 6, 8, 10, 12, 14, 16. You gotta make 2 more, and I'm gonna actually put them on this sulfur here. So what that's actually gonna do is it's gonna make this into a bent molecule. It's kind of like water with that those lone pairs on the oxygen, but this actually is polar because the molecule is bent. There is going to be more of a concentration of negativity on this top side. And lastly, xenon tetrafluoride. That's just a xenon with 4 F's on it. Yeah, this is tetrahedral. It's the same atom 4 times, same electronegativity here, like arrows like that. And bond angles are all even, so this isn't polar, it's symmetrical. So the answer is NO and SO2. Can't really say that. NO and SO2. And that corresponds to answer 5 on your test.